Okay, so I'm gonna present my Earth-like exoplanet project. I believe alien life is quite common in the universe, although intelligent life is less so. Some say it has yet to appear on planet Earth. Stephen Hawking. Here's a quick little introduction. There are a lot of Earth-like exoplanets, and they share a lot of the same properties, characteristics that make them Earth-like. Yeah, so with that being said, it's been years since humans have tried to look for exoplanets and lives, especially high degree intelligent lives on the exoplanets. And I believe they haven't yet found one, but what they have found was obviously what we're going to talk about, Kepler 452b, one of the exoplanets that is, say, the most Earth-like. Did you know this? Despite all the other factors like temperature, water, and atmosphere, by atmosphere I mean the structure of the gases in the air, say like oxygen and nitrogen, whatever. In order for a planet to be Earth-like physically, it has to be in the right size because size is often considered a most, say, significant factor. And mass can be used to describe a planet's size more accurately and physically. And radius is also a factor to, cover the mass. Last but not least, the center of orbiting should be a sun-like star. First and foremost, mass is very important, and we know from the famous Albert Einstein equation, energy is proportional to mass. What that means is that from the previous slide, we know that the the Kepler 452, the sun-like star in the center of orbiting, is 10 times larger than our sun. What that means is that with that 10% larger in mass, it's got a lot more energy and it's much brighter than the sun and it's also much older than our sun. With that in mind, we also know that um, the weight is proportional to the gravity the planet has. So the surface gravity on Kepler 452b is apparently 2 times as large as the Earth because it's got a much greater mass itself and a different radius. What that means is that everything would be twice as heavy as if it were on Earth, just like this. Then from the Newton's universal law of gravitation and the circular motion formula, we know that radius and velocity has a distinct connection in between each other that we'll cover in the very last few slides. Here are some stats that I gathered from NASA's website and also the Wikipedia page. So obviously the the other reason that NASA called Kepler 452b the most Earth-like exoplanet is because of its almost identical similarities to the Sun and Earth relationship because it's got pretty much the same distance, only like 0.04% off, and the mass is just 2 times bigger. Well, I mean, yeah, I believe. And the initial tangential velocity for it to be a Kepler 452's moon is not too much. I mean, yeah, and they are all going to be used in the later calculation that is more detailed and thorough for sure. Finally, we have orbit period. In order to get orbit period, we know that the period is just the amount of time it takes to go around one revolution. That is 2 pi r over v. 2 pi r here is the circumference of the orbit, while the velocity here is just the tangential velocity that we got from the equation earlier. For this slide, I'm going to cover something about orbiting. So according to Kepler's first law, the orbits of all planets are ellipses with the Sun located at one of the ellipse's foci. As for Kepler 452b, its Sun is the Kepler 452, a G-type main sequence star located about 1,800 light years away from Earth. That is a lot of distance away. What that implies is that we cannot see it using our eyes by the telescope. And the orbital radius between Kepler 452 and 452b is 1.46 AU, which is what I said earlier. That's basically the same as the one between Earth and the Sun. And that's just how orbiting works. As for a period that I'm also going to cover in later calculation, the time it takes to go one revolution for Kepler 452b around 452 is 384.8 days. That is really close to a year on Earth. Here are the detailed steps to derive that equation. We start off with universal law of gravitation. We also know that for any radial acceleration, as of what we talked about in circular motion, for the acceleration, it's equal to v squared over r. That is, in our case, the gravitation. We also know that one way to calculate the force of gravitation is m times g, while the other words to actually interpret the force of gravitation is that we can use Newton's second law, because the unbalanced force, in our case, the gravitational force, is equal to the mass times acceleration. Anyway, we just set the above equations equal to each other and cancel the small m, which is the mass of the planet, and one big R, the radius, the orbital radius in between. And we get the equation that we actually used to calculate the tangential velocity. And here's the detailed steps to calculate the answer using decimals. And here's how I actually get the period by myself. Since the period is just the amount of time it takes to go one revolution in the orbit. So basically that is the 2 pi r the circumference over the tangential velocity. But we also have to account for the units for time because um, for velocity it should be meters per second, while um, generally for the period that we use for exoplanets it should be days. So yeah, I accounted for that as well. Just like what we did for the modeling Jupiter's moon Io in class, I used interactive physics to model the Kepler 452b's orbits. As you can see on the right, it's a short video, 20-second video that I was actually, um, was trimmed from a 15 minutes video that I got from interactive physics. Like I just sit there and got this video and trimmed it using time lapse to speed it up, and here we are. After all those, I think I really hope that someday we can actually find something organic on Kepler 452b.